Hi, everybody. Welcome to Ballroom A. We have here a session called Design Pressure, and I want you all to give a warm welcome to Hynek.
Good afternoon. So, as just said, I'm Hynek. I'm a software engineer at a boutique German web hosting company called Vario Media. My boss told me to not call us small anymore, so. I'm also a burned out open source maintainer and future famous YouTuber. So you got a chance. You knew me before I was cool. So I'm here to talk about software design and how there's pressures on your precious applications that you might not be aware of that affect your design in ways that you might not like. But first, let's make sure everyone is awake. So, the use of object relational mappers and class-based validation frameworks ruins your project. How's that for a hot take? So in YouTube land, we call this an attention hook to stop people from closing the video for the cursed retention graph. And depending on whether you deliver on it or not determines whether you are a great filmmaker or a scammy baiter. So let's see if I can pay down that bait debt and see in what group I fall. Let's start with adding a tiny bit of nuance. So Django and SQL Alchemy and Pydantic and Marshmallow and whatnot, they're all fine, as long as you're aware of what effect they have on your code. And that's today's topic. But the concept of design pressure is not specific to this area. So I will use other examples that have nothing to do with those two. So to be clear, there will be something in here for everybody. I just want to have something concrete to hang my head on. And this is not a talk about tools, this is a talk about architecture. And therefore, I'm also not here to tell you to stop using your favorite tool. So you can relax, you can stop messaging Mike and Samuel, and the Django Software Foundation doesn't know where I live anyway, so don't waste your time. My emphasis is not on ORMs or validation frameworks, my emphasis is on the unreflected. So my goal for today is to make you aware of the trade-offs that you're making, and it's trade-offs that you're most likely doing subconsciously. And as good old Carl Gustav already knew, this is not great for you. Design decisions need to be deliberate, not a matter of perceived fate. And, but to get there, we have to clarify one thing first, and it is, why do we write software? Other than for money, of course. Is it to access a database? Or is it to validate some data coming through a web API? Probably not. I'm sure there's someone in here who does exactly that, writing some database driver or something, but usually it's not. We usually write software to achieve a goal using those two tools, and the core logic that does that is often called the business logic. And as with everything in software engineering, there's a passionate discussion on what exactly is business logic. But this is my talk, my room, my rules, and for me, it is the code that determines what to do based on the data coming from the database, some kind of user input that can be a form or a web API in this case. And most importantly, business rules. And the term business logic harks a little bit back to the times of where computers were huge and only stood in banks. But your business might also be curing cancer. Business logic does not have to be about shareholder value, as we've learned today in the keynote. I was a little bit afraid of making political statements, but I feel a window open to significantly this morning, so. But in many cases, business logic is just a bunch of if statements that are buried somewhere in a web view or a CLI endpoint, mixed up in form validation and database access. So, and for those standing in the back, there's a lot of space in the middle, so nobody has to stand here, there's still a lot of space. So this is especially true for tutorials that make you implement simple block engines or to-do apps, famously, because they're teaching you a framework. They don't want to distract from the framework. They're teaching with complex out-of-framework logic. And things that many beginners haven't ever seen explicit business logic in their whole lives. But it is the code why the application ultimately exists. So it is the code that can have grave real-life consequences to actual living humans. Like when you're using the wrong radiation dose. Like I hope every programmer has heard of Therac 25. It is a radiation therapy machine from the 1980s, and it's famous for having a race condition that caused some patients to receive 100x of the radiation they were supposed to get. As you can imagine, our mushy bodies don't deal well with that, so people literally died of that. And maybe people want to die of the radiation overdose if you screw up your business logic, but it might still translate into real-world calamities, like the recent British post office scandal, where Fujitsu accounting software accused innocent sub-postmasters of stealing. 900 of them were prosecuted for theft, fraud, false accounting. 236 went to prison. And the fallout on their private lives was even worse, of course. So the business code is the most important code of your application, and you have the moral imperative and self-interest to make it as correct as possible. And that's where design pressure comes into play, because it can make that job harder or easier. And I've encountered this term for the first time in J.B. Rainsberger's seminal talk, Integrated Tests Are a Scam, or it used to be also called Integration Tests Are a Scam. And he talks there about how growing the scope of a system under test, so for example, instead of testing a class, you test a whole service layer or end-to-end, you limit the design feedback from your tests about your code. So in other words, it's masking the pain of a bad design. In other words, you get away with highly tangled, highly coupled code because you don't feel the pressure in the form of pain, the pain of testing coupled code. Now, what exactly is coupling? Two pieces of code, for example, classes, modules, whatever, are coupled if they can only be used and understood by looking at both. Changing one usually forces you to change the other one too. So coupling makes it harder to test, change, and understand your code, which is really bad in the long run. I mean, you shouldn't have to understand the intricacies of an ORM or Cthulhu forbid a web framework when trying to understand the logic that decides on the amount of radiation you're gonna blast at a human being. And since you're all writing tests the whole time, you get the feedback that your code is too coupled from the get-go, not like 1 year later when your boss wants a new feature and you don't know how to add it because you have to change 5 classes in 6 files. Or when hectically trying to debug your code because something terrible happened and you might go to jail. Ask Volkswagen. So this point has been made many times before. Testable code is better code because it forces decoupling on you. That's the pressure. And while there is the concept of so-called test damage, which is complexity in your production code that only exists to facilitate the stability, and clearly too much of that is also bad for you, overall testing is a force of good. And this is our first test pressure of the day, and it's the good one. Having to write tests without monkey patching and mocking half of the universe leads to a less coupled code by being painful if you don't do so, which makes the code easier to change and understand, which is good. In fact, I've heard the arguments that the main function of writing tests is specifically the design pressure for better software design, and the tests themselves are just a nice side effect that you just didn't delete afterwards. And I wouldn't go as far, but they've got a point. So I hope this part was relatable to everyone, because it doesn't matter what kind of code you write, we all run into testability pain. It's natural. Acknowledging that pain and letting it guide you instead of claiming that you're the one snowflake whose code cannot be tested will improve almost everyone's life. So pain, in this case, good. Next, we'll look at a design pressure that's neither good nor bad. And I will use a great talk I saw at PyCascades 2024 to illustrate it. It is called The Rising Sea. And in it, Matt Drury shows a very elegant solution to a problem from advent of code, our beloved tradition of vowing to use it to learn a new language and giving up on day 6 because, surprisingly, this year too life is too stressful. It's too much work, but next year we will run Rust. So he frames it as a conflict between two mathematicians, and I recommend everyone watching it because it's both entertaining and enlightening. And I will not spoil the entertaining part, just the educational one, which nobody cares, the fun. So your input is a harbor with stacks of boxes, okay? Like the letters in square brackets are boxes, stacked on each other, and each stack has a number from 1 to 9. And then you have instructions telling you what to do with those boxes, like move 5 boxes from stack 4 to stack 9. And then, channeling one of the mathematicians, and I'm not going to tell you which one, he gives himself a design maxim. You should structure your data so that the problem solves itself. And then he goes off to model the problem using nice, clean classes. So, an instruction class that encapsulates a move. A harbor class that consists of stacks and executes instructions. And finally, a stack that consists of boxes and allows you to add and remove boxes to and from the top. All very straightforward code, I'm going to say. The boxes themselves don't matter. It's just some object represented by letters, so it could be just strings. It doesn't matter for the problem. And these classes combine the business logic of harbor box management with the data structure to work on. This makes it the domain model. And a domain model in software engineering is the conceptual model of the domain that incorporates both behavior and data. A conceptual model in Python is a very hand-wavy way, just a fancy word for a bunch of classes and how they relate to each other. And a domain model tries to reflect the domain in which you're solving your business problems. In this case, a harbor. Meanwhile, a data model is something completely different. It's, for all intents and purposes, the database schema. And it annoyingly sounds almost the same, and many people can't literally tell the difference between those two, because often they have never seen a domain model, in fact. This is like one of the biggest sins of software engineering, is like this constant reuse of terms. It seems like all important concept names are somehow permutations of the terms model, event, domain, and service. Look it up, it's true. Anyways, this is your precious. It's a domain model, no matter how small, and it tends to be on the small side compared to the rest of the application, ironically, is the reason why your application exists. And coming up with a domain model is called domain modeling, and the quality of a domain model is a function of how well it reflects the domain and how understandable it is, which I think Matt's code delivers on totally. Like, it even fulfills the platonic ideal of a domain model by being completely isolated from everything that is not part of the domain. On one look, you can identify the entities and their relationships and understand the business logic they implement. It doesn't even need conditionals like if statements, which is always a very good sign, because they always add a lot of cyclomatic complexity. Now, we've got this pretty cool domain model that is just a bunch of classes that implement your business logic without knowing how they got created or how they are persisted. But then, as a plot twist, he shows us more code. And this code he calls the darkness. Please don't try to understand it. So this code is necessary for the elegant code from before to do its work, because it parses the input that you get from advent of code, and it munges it into nice and clean harbor objects. But this code has nothing to do with the problem domain, like not at all. This is just a parser. And the actual crane moving code only gets to be elegant because it knows nothing about this filth. So, in a way, this is a buffer between the data coming in and the business logic. And Matt concludes, the shitty stuff should happen on the outside layer of your program that interacts with the outside world. Once it's inside, organize it into nice data structures so that operations, i.e. code, are as self-evident as possible. Beautiful. This is the key lesson. Like, it's just another way of saying to validate at the edges and also kind of don't validate but parse. And he also goes a step further and says to reshape your data at the edges too, such that it serves your problem. So this buffer between layers, it doesn't have to be a parser that you wrote yourself. It can be a function that takes the input from another parser, like Pydantic, and transform it into beautiful harbor objects. Or it can be some kind of database access. It doesn't matter. What matters is the data is coming in, and you're taking agency over the shape of the data before you work with the data. Because what we've seen is that the shape of the data determines the shape of the code. That's design pressure right there. And if it makes parsing with executing, this code would be much worse, and the business code would be much harder to understand or even to find in the first place. But Matt removed this pressure completely by converting the input into something that is well suited to his problem first. So the business logic is completely decoupled from parsing. The shape of the input that you have no power over has no influence on the shape of the business code. All right? So as promised, still no ORMs or validation packages. This is relevant for every single one of you. This is like computer science 101, but we don't talk about this anymore. But with this in mind, let's talk about ORMs and validation frameworks. And They both tend to call their classes models, which fair enough. As I've said before, there are like 5 terms you're allowed to use to name things in software engineering. But those models have wildly different design goals, conflicting goals. The shape of validated data is dictated by the shape of your API, which is shaped by whatever your users want to use to achieve their goals, or maybe by some API best practices like JSON API or stealing from another popular API. What people want to post is almost never what I want to work with. Then the shape of ORM models is dictated by the shape of the data model, aka database schema, aka table design, with various levels of adjustment power depending on the ORM. Like especially SQL Alchemy has a lot of offer to munch table data into something convenient. Django's ORM has a pony. So a database schema has a very different design consideration than an API schema or a domain model. So for SQL databases, there's always the tension between performance, normalization, and redundancy. In old school companies, they are even designed and maintained by dedicated and usually grumpy DBA teams that don't care about your business code at all. All they care about are indexes and dead tuples. And fair enough, that's their job. And finally, your ideal domain model is dictated by the shape of the problem that you're solving and nothing else. And since it's the most important code in a project, you ideally want to get all the help from your language and your ecosystem that has to offer to get it right. Like making illegal state unrepresentable or static typing is great. And it's a design pressure on its own, as Lukasz told us 3 years ago in his wonderful keynote. And that gets really difficult when, for example, Django's ORM forces you to pass strings to name the fields if you don't want to overfetch in model objects.values. And there's not much hope to make that ever type safe. So, and if you don't think overfetching is a problem, a Django adjacent friend of mine told me the other day that someone found out the hard way that there is a limit of 1,664 columns in a Postgres query. Careless joins, wild denormalization, and not limiting the columns you need will do that to you. So my business code also needs different kinds of information depending on the state the entity is. Like I'm dealing a lot with our invoicing right now, and I care about very different things when I deal with open, overdue, or paid invoices. When dealing with open ones, I want to know when they're due. When they're paid, I care about when they've been paid. And finally, when dealing with those that are overdue, I start caring about how long have they been overdue and how much reminding has been done to them in the meantime. Especially when dealing with overdue invoices and deciding whether to start debt collection on real people, the focus shifts completely. Like, you're still looking at the same data from the same source. But you probably need to enrich the invoice data from other sources too. You need to compose your ORM models, or even call a third-party API to verify something. And since this code can have devastating consequences, I want my business logic to be as straightforward as possible and my data structures as clear as possible. I certainly don't want like one generic big blob with a lot of magic full of optional fields here. And having classes with a lot of or none type annotations is like one of the biggest design symbols there is, and one of the biggest gifts typing gave us, because you can see on one side, when you look at a class, okay, something's fishy here. Again, some packages offer ways to make this problem less severe, like tagged unions, table inheritance, or field aliases, but they are underused, strictly advanced features, and they usually still fail on the last mile when things get really complicated, which is where they would be most important, right? So how do people usually deal with this conflict? The most common approach that is kind of bad is, depending on your preference, you pick the web API or the database schema, but never the domain model, as your primary model and let the rest conform come hell or high water. And when starting with a database, there's even a fancy name for that, and it's database-driven design. Which, by the way, is meant as a pejorative. It is not a best practice pattern, okay? Do not write this down. Either way, it means that you're in any case, you're starting on the back foot when implementing business logic on what is essentially raw data coming from somewhere. And or additionally, a web API that allows me to guess your database schema, and or a database schema that would make anyone with a background in database design take up sheep farming in Montana. Yes, Banner was a DBA before he saw your database schema. You heard it here first. Anyway, that was the middle bad guy case. The worst case is you balance the needs of the web API schema with the needs of the database schema. Maybe because you want to use the same models in both because you thought that it's a good idea, it's less typing. And you're getting mediocre results already because those two layers also have conflicting goals, right? So you have already a compromise. And then you force the resulting full compromise on your domain model, meaning it's impeded not by one impedance mismatch, but two. And this right there is the reason why I personally find the combination of ORMs and class-based validation packages so unholy. The domain model that is foundational to the quality of your business logic is squeezed between two layers with conflicting goals that lure you in with convenience, promising you the dream of a unified data model across all layers. And this is the result of the dream. It's more of a nightmare when shove comes to push. It's the other way around, right? Third language. So if the shape of the data shapes code, weirdly shaped data shapes your code in weird ways. And it can't be anything but weird, given it's dictated by a compromise between the database and the web API schemas, which also have conflicting goals. But again, this is not the fault of those tools. This is not about tools. This is a systemic problem of trying to force a unified model on layers with conflicting goals. But wait, it gets worse. In theory, with API versioning, we can change web API details anytime. In theory, with database migrations, we can change the database schema anytime. In practice, they calcify the shape of the already imperfect data because changing web APIs angers users. Nobody has the time to adjust their API calls. And database migrations are still tedious and problematic, especially under load. No matter how good the tools are, they're still like laws of nature. And my experience and what I've heard around is that the circumstances tend to lead to a loss of control over your database tables eventually, if you ever had them in the first place. And since greenfield projects are very rare, actually, this is like one of the dirtiest secrets in IT, I feel like. You never get a greenfield project. This means that you almost never get to design those models. And if you take this to the logical conclusion, it means that if you let all this happen, you have lost control over your domain model. And since the shape of the data shapes your code, you've also lost control over your business logic, which is bad. And while this topic was like marinating in my head, and I was just telling my friends over beer the same thing all the time, one Adam Montgomery wrote a blog post entitled "How I Build," which refreshingly, despite coming out in 2025, was not just AI bootlicking. And it had this killer passage that matched my experience and I found very liberating. So it's okay to have duplicative-looking types for different layers of a project. For example, ORM, API schema, and business logic. Types need to be easy to change and reason about, so we can adapt them to our evolving requirements. Types near the edge, like API schemas and database tables, are inherently less flexible. It's often better to explicitly map types between these layers rather than create a Frankentype and allow the least flexible layer to calcify the rest. Wow, so this is my talk in one slide. It was almost spooky to stumble over it while I was thinking about these whole things. Like map types here just means convert to better types. So what he's saying is that you should be okay with having 3 classes for the same thing, depending on what you're doing with the thing. And I'm going to add that it's okay to have even more, as I've shown in the example with the invoices. Now, who would like to see an example? Yeah, right, everybody. I will show you something, but as Kent Beck once wrote, good examples are by far the hardest part of explaining design. Because it's usually we can't just take something from production because A, copyright and getting fired, and B, they usually only make sense in the context of a larger system that we definitely cannot share. But let me try anyway, and I will use something very banal, and it's the international postal addresses. So given there's countries where a postal code is enough to receive mail, like Ireland, that in 2015, after being the last country in the OECD to not have postcodes, decided to go all in. And given there's countries that don't have postcodes, and I'm sure there's people in Ireland who refuse to use postal codes out of principle too, because it's probably politicized, every field of an address is optional. Now, this is not a domain model, this is a data model. Now just add an ID, and you've got yourself a database table. But this is not useful at all when trying to write any kind of business logic around this or trying to validate an incoming address. I could use a dictionary instead of a class here, and I would lose absolutely nothing. Just imagine trying to add any kind of behavior to this class. You either end up with a quagmire of if, is, none statements, or you end up with some kind of dispatch on the country field, but you still have to fight the type checker the whole time. So, assuming you're writing some kind of code where the shape of the data matters, for example, formatting addresses for printing on envelopes, which emphatically is not business code, but it matters there. You can hide the different valid shapes somewhere in the code in a Rube Goldberg machine of if, none statements and match statements and whatnot. Or you can make the shape explicit and define them like here, for the US of A. Looking at a US address, you know exactly what fields exist. A function that takes a US address as an argument knows exactly what it's getting. It's defined in code and validated by MyPy or TY or whatever checker you're using. You can use all fields without checking first, except adder 2. It's right there. Yeah, it's black on white. And to be clear, there's totally are ways to get this out of a pydantic model. I know that. You just have to know that you want that. This has to be a goal for you. And you can also totally pass 6 arguments to a function. Nobody's going to stop you. Arguments that have the correct type annotation. You still have to fight the type checker once when invoking the function. But once you're inside your important code, the type checker is your ally again, right? So it's, again, there are many edges in your code. So what I'm actually suggesting for you is not to ditch all your tools, but in an ideal virtual case, you would start with a domain model and you accept the conflicting goals of all 3 layers and adapt the data to its optimal shape for each case, understanding there might be more than 3 shapes. In the case of a database, this could mean applying the repository pattern that uses the convenience of an ORM to build database queries, but spits out neat and clean data classes, address classes, with encoded state and nice types, and as few optional fields as possible. And they are decoupled from the ORM too, and therefore from any kind of I/O, which makes them easier to test, which takes us to design pressure number 1. There you go. But of course, as you may have noticed, we don't live in an ideal world. And this is software engineering, which means it depends, and we are talking trade-offs here. There's plenty of use cases where the application would consist 90% of data conversions, which is not ideal either. But you definitely need to start with the domain model because you need to understand your problem domain, like the harbor in my example, and you need to understand what your software is supposed to do using what data and what shape of the data is ideal for the problem you're solving. Because if you want to compromise, you have to know what you're compromising on. But then, when you know what you'd like to have, you do start to compromise. But you're aware of what effect or design pressure it has to pass a pydantic or ORM object into your business code. And then you need to decide, is the convenience worth it or not? Often it is. Sometimes it's not. You can compare the performance trade-off between mapping data into a better shape versus implementing algorithms on top of suboptimal structures. That's a thing too. You can look if the tools that your ORM or validation framework ship can be used to shape your objects closer to what you'd like to have if you can't have it outright. But first you need to know what you would like to have. But either way, you're doing it in a conscientiously way and you know your options, so you don't call the result fate. Unfortunately, what I see a heavy influence, though, is pure laziness. Laziness leads us to papering over impedance mismatches with accidental complexity, which is complexity that is not inherent to the problem you're solving. So laziness can be great, like when it makes you automate repetitive tasks. But this is the wrong type of laziness, because we are taking shortcuts here. Shortcuts that avoid having to represent entities in more than one shape, avoiding to press more keys on our precious mechanical keyboards. But then we have to pay for that later by having a lot more code paths to test and consider, because every if statement doubles the number of possible code paths. And that makes code harder to understand and to have a mental model of, by having awkward data structures in places that matter, by dealing with business code that is somehow coupled to cache implementations. I've seen that. or by not being able to adjust your data structures to a new understanding of the problem you're solving. And this makes proper design a delayed gratification, which humans are famously bad at. So where does this all leave us? Your business code is important, but if you haven't put any thought into it, it's probably buried somewhere between form validation and database access. Go and find it, and make your data structures serve it. Maybe try it out, like domain modeling, maybe in a related thing like Sans.io in a toy project. Just play with it. Then keep your tools, but try to decouple your business logic from them, learn them properly, find ways to limit their design pressure on your code. And finally, writing tests will make your software better. Stop monkey patching, as Brandon Rhodes wisely quipped, it's software bankruptcy. And let the pain guide you to less coupling instead. And that's all I have for you today. If you want to go deeper, this link will take you to a collection of articles, books, and videos, and of course, the slides that you want to ask me about. As you can imagine, this is a wide field. And if you just got this stupid joke and therefore speak German, get your domains from Varo Media and web hosting too. They paid my way here. They leave me the time to do things properly and share my findings. And of course, follow me on all the socials. In the brave new world, there are too many to put on one slide. Here we are. So check out my homepage and pick your favorite. And finally, if you like my sexy Czech German accent and want more of it, like and subscribe my YouTube channel. I'm very slow at publishing. I've been called the J.R. Martin of YouTube twice today. But people do like it. And I'm only roughly 7 million subscribers away from TGP grade. So I need all of you. And with that, I'm Hynek. Thank you very much.